Good morning, ladies and gentlemen. I'm Jonathan Berte, founder of Robovision, and in today's talk, I would like to share with you some insights into how we're deploying scalable deep learning systems in the industry and beyond. But first, some key facts about who we are. We are Robovision, and we started as a normal robotics company in agriculture, adding machine vision as a key USP to the mix. We realized that writing robust algorithms ourselves was not easily feasible within this field of God-made products. So we decided to make an AI SaaS platform company based on advanced deep learning architectures. We're with a team of 70 people based in Ghent, Belgium, and still completely owned by the original founders. We focus on visual data, both in 2D and 3D, in four distinct verticals. We started pioneering deep learning in agriculture about 6 years ago, based on Theano at the time, where we now have a global footprint. We moved to manufacturing soon after. Healthcare and smart cities are quite new in our portfolio. All of these verticals have one thing in common. They require scalable deployments and on-site retraining of new datasets by machine operators. In fact, there are several key challenges when one tries to industrialize deep learning. So what's the real deal with industrializing AI? Well, for some part, it's because the conservative industrial world is not a great fit with the open and fast-changing AI Python ecosystem, tweaked for rapid prototyping and information exchange. Machine builders usually require 5 to 7 years guaranteed hardware support, whereas TensorFlow and Python often evolve with breaking changes. They also want to retrain existing machine learning models with new data and label rapidly and efficiently. And they want to have access to the latest and greatest papers and do not bother whether they publish their code in TensorFlow or PyTorch. Robovision is merging these two worlds at the other end of the spectrum by insulating these hard requirements from industrial users that do not want to be bothered by all the peculiarities of updating machine learning frameworks. So we took all of these pains and defined a no-code platform should look like in a machine learning context. Not really easy, obviously, as you might expect. It took some iterations to come to the right value proposition. RVAI, the Robovision AI Platform, a no-code environment that supports the whole customer journey, from visual data onboarding to scalable model deployment, on your cloud of preference or on your on-premises cluster. We democratize AI by making advanced machine learning creation available to all while not making any concessions to experts. They keep the freedom to implement their custom Python code in their framework of choice. Furthermore, they can use their favorite cloud platform, as we standardize in Kubernetes Docker for scalability. As you might have expected, many of the foundational cornerstones in RVAI are based on Ray. Now let's go back to the core. What happens in a typical deep learning project? I'm using the terminology deep learning here because from our perspective, it refers to generic deep architectures like UNet and ResNet 50 that are applicable in many use cases in distinct application areas. A well-annotated dataset is often more important than the last tweaks of a loss function. Algorithms automatically created with less and less supervision. That's the real promise of Joshua, Jeffrey, and Jan, the godfathers of deep learning. Due to the specific nature of convolutional layers in the deep net, they act like custom image processing kernels for vision algorithms. Before that, it was the task of the vision engineer to select and tweak his own kernels, like GANnyEdge, some of you know. The most interesting part is that these consecutive image processing steps are surprisingly similar to what happens in the visual pathway of our own brains. You could say that deep learning set into motion a real revolution. The old von Neumann paradigm of a single processor and its memory are rapidly vanishing in favor of more hardware-supported parallel compute, mainly driven by the success of deep neural networks. Reality can finally be segmented in a more robust way, a dream that was long due in the image processing community. At Robovision, we implemented these typical challenges at scale. Data can be onboarded in a generic S3-like way, wherever its location. The consecutive labeling session can be sent anywhere, automatically activated in an Azure data center near the labeler for low latency when, for instance, a radiologist needs to annotate lungs. Automatic grading of annotators is done in the platform to make sure that all of the data is curated in a good way. Underperforming annotators are detected automatically by analyzing their behavior with the help of machine learning. Ultimately, the supervisor can start a scalable training session on a GPU cluster of choice. The loads are optimally distributed with the help of Ray. The typical iteration to success is centered around labeling, training, and retraining, done by non-data scientists. We didn't invent this platform overnight. Our customers did, by asking the right questions, as is shown in this extract from a BBC World documentary about AI. In the beginning, we were naive. We thought we could just make a human-engineered one-size-fits-all algorithms to plant cuttings with the help of robots and cameras. We were obviously wrong, and our customers pushed us into the Theano era of deep learning. It must have been about 5 years ago, sometime before TensorFlow and PyTorch saw the light. The machines had to be super flexible, be easily trained on new plant types, cross them reliably out of a pile on the conveyor belt. It had to be faster and cleaner than the human way to make the business case really work. We had no investors and no subsidies at the time, so we had to excel in a compact but efficient way. And so we did. Soon after, we could sell hundreds of machines in an AI platform as a service-like way, with yearly recurring revenue. Small and big companies in agriculture located as far as Sydney in Japan are paying yearly fees to use our AI services, enabling us to grow with triple-digit numbers without external investors. Some of them created hundreds of algorithms and almost consider the machines as part of their team. In fact, we banked on this psychology. We integrated Walt with a face into a real production situation at Audi Brussels. Walt knows his co-workers, and because he's using face recognition, he knows that only the supervisor can change the actual production type. He understands gestures and smiles when the production is running at 100%. But let's go back to a core question in this talk. What schemes do you optimally apply when you want to truly implement maintainable and scalable AI systems? For that, let's take a look at the common practices nowadays. You did your PhD, you start working for a multinational. Python-based machine learning and deep learning is pretty fresh and not so compatible with many multinational IT practices. Employees often start experimenting with Python notebooks they get from machine learning papers on arXiv. They browse to published code on GitHub and apply it in their specific context. The problem is that another group working on a different topic in that same multinational also finds a good paper that initially shows promise, but it's implemented in a different framework. As projects become more ambitious and complex, different groups need to work together, building hybrid machine learning systems, where, for instance, the object detection code contains TensorFlow, where the tracking part is implemented in a state-of-the-art PyTorch model. That's where the Robovision SDK, with Ray as a foundation, comes into place. The core philosophy is that every machine learning algorithm can be considered a Raylet inside a Docker cell. And the SDK is built in such a way that it can be easily glued together, like a pile of Lego bricks, easily joinable into an efficient pipeline for a new use case, built on Ray, for instance, for high throughput and low latency. Let's make this practical with an actual use case that we implemented, the large-scale processing of graphic streams. You have a highway, a lot of cars, and we have to derive actual facts from the flow of data to optimize the operations. People in the control room need to know the average speed, the intercar distance, and anomalies like which specific cowboy is making the road unsafe. In the old days, without Ray, we had to implement a custom Python multiprocessor environment, taking care of things. But basically what we got is machine learning modules depending on a Python global interpreter lock. So it was practically very hard to parallelize those models into a truly concurrent framework, also taking care of the available GPU resources. In the traffic example, the total processing time of the pipeline is a reciprocal of the sum of the times of the module in that pipeline. In this case, the RTSP stream. The frames are first processed in the object detection cell, takes 50 milliseconds. Afterwards, it goes to a tracker model, and finally, two models are spotting anomalies and calculating the speed. It ends up on a dashboard in the traffic control center, where it can run at 5 frames a second. Way too slow for traffic applications. And there is another drawback. It typically has to run on the same hardware platform because of Python. So we also have a potential scalability issue there. Or we need to clone everything on different machines, of course. Thankfully, after a long and detailed search where we evaluated Dask, Rain, Timely, Luigi, Faust, and Wallaroo, we finally decided to implement Ray as a scaling component inside our platform. Ray is now becoming the preferred distributed execution platform for experts in the Python ecosystem. It makes it easy to scale your machine learning pipelines and to leverage state-of-the-art machine learning libraries. We substituted our custom-made multiprocess environment with Ray actors, and all of a sudden we could reach a much higher frame rate due to maximal concurrency. The processing time per frame is now only reciprocal of the slowest cell, so we get 16 frames a second instead of 5 without Ray. So why Ray? Apart from the parallelization paradigm, it also handles GPU resources exceptionally well, taking the cost down of typical scalable machine learning deployments. We implemented Ray in a pretty straightforward way. One machine learning model equals one Ray actor. And one customer deployment is a singular Ray cluster with multiple host worker nodes. This moment we're adding custom resources to the nodes, so we can work with different Conda environments. With this foundation, machine learning models can be stacked together as Ray actors that can be more optimally distributed over a larger GPU cluster, an excellent foundation for traffic use cases. Our customers can quickly configure new pipelines into new use cases without writing a single line of code. It can be maintained and retrained on new data by normal IT operators. No need for an extensive data scientist team. Experts can now implement their custom cells and regroup them into arbitrary pipelines. One important aspect of scaling up a typical deep learning use case is at-scale labeling with supervisors and measuring the label quality. Speed and efficiency are very important in big projects with potentially millions of images. To increase speed, the labeling needs to be fast and make suggestions of which object to label. You could consider it as a sort of Photoshop in the context of machine learning, with predictive labeling and magnetic lasso tooling to annotate faster. Of course, different contexts require different tooling sets. When we want to prune plants with robots and AI, we need to be able to present a 3D structure as a point cloud, obviously. Similarly, when labeling pics or DICOM CT scan data, we need specific tooling tweaked to that context. We're also integrating with third-party tooling, for instance with Infusion, a best-in-class DICOM 3D manipulation technology company. When one tries to democratize technology, ease of use is an important aspect. And with the SDK, machine learning developers can create templates that can serve as easy workflow wizards, taking you through custom data and model manipulation journeys. One important aspect of the platform is the AI store. We see that it's a key thing in the democratization of expertise. Our mission with Robovision is to facilitate the access to expertise in a similar way that the Apple App Store and the Google Play Store facilitate development and global access to mobile applications with their marketplaces. It could lead to better healthcare for all if a tumor of a patient is analyzed by the best radiologists on earth, regardless if they're human or not. The funny thing is that the core concept of the AI store was not invented by our team, but by our customers. A few years ago, they started selling Robovision models exported from our platform on USB sticks for thousands of dollars. We immediately saw the opportunity and started working on a way to ease model exchange. It could also be a way to work more optimally in a research institute or a multinational as an internal collaboration platform. It could be an MVP marketplace for spin-offs. In a B2B context, it can be a data monetization tool. A Dutch tulip grower could, for instance, monetize his tulip model in another continent. And for robotics companies, new use cases can be rapidly implemented on robot systems of choice. On-site, efficient, and no-nonsense retraining on a new product type is a cornerstone of robotics use cases. Now let's go to the second part of this talk, the actual Robovision on-the-Ray scalable AI use cases. As mentioned earlier, we started in the greenhouses some years ago, and we quickly realized that on-site retraining of algorithms was quintessential to a better platform adoption rate and a lower customer churn. Operators shall just have minimal interfaces and giving the right examples to the artificial brains of our platform. It has to be fast and no nonsense. And in fact, this customer named Florensis has in the meanwhile created more than 400 deep learning models to plant cuttings. Dailyfloor even has a robotics farm with more than 30 robots. 2 operators are doing the work of 60 FTEs. What we see is that due to the specific situation in the US with lower salaries and Europe, the degree of robotization and AI is higher in Europe, as is the robotics expertise companies like ours. We didn't limit ourselves to 2D imagery with deep learning. In the north of Holland, we're planting flower bulbs by automatically labeling them in a cat-like environment. We point out to the right growing direction by sketching an arrow in a 3D environment. Distributed training afterwards happens efficiently with the help of Ray. Our robots are planting more than 10,000 tulips an hour, and it requires excellent logging and user interfacing to know what went wrong in the case of a production anomaly. We didn't talk about AI on the edge yet, but we compiled and tested Ray on the NVIDIA Xavier last summer, and we're in sync with the Ray team to create the necessary CI/CD for prolonged support. In this case, an AI-enabled drone is scanning a potato field with a hyperspectral camera in order to spot potato plant diseases. As usual, data is being labeled by the crowd in order to efficiently train the deep neural nets with enough data. In another use case, a robot needs to automatically prune roses, as used by rocket farms in Salinas, near Half Moon Bay, California. For each new plant type, the main stem is labeled by operators, as well as the optimal cutting points. After a transfer learning session on a Ray cluster, the robot can start cutting on site, as seen in this video. We will now go in a bit more detail on our platform to explain you how this is done in our software. You go to the admin section of the dashboard and you create a new pipeline. You label and train a new model. This brings you into a no-code flow. It sets up all the components and initiates the labeling sessions. When the labeling has been done, we can start training. The Ray supervisor actor spawns training actors and they are optimally distributed among the available GPU resources. Due to the highly generic nature of 3D deep learning, we're bringing other machines to the market this year with our joint venture together with ESO Group, the DNA sampling robot and a 3D deep learning based sorter. All kinds of plant aspects can be graded automatically based on the 3D morphology of the plant. As can be seen in this video, we can measure the size of the plant parts and sort them accordingly. AI is of massive importance in retail due to the large inventories involved, and Robovision proved to be pioneering in this space. with supermarkets that are using our cash desk-based deep learning-based scanner to automatically recognize the correct fruit and vegetable types. So the operator no longer has to scan the code or type in the numeric code to weigh the fruits. New products can be trained in at scale during the night by supermarket operators. Inference by day, training at night. An important aspect of our portfolio are AI safety applications. For instance, in this crane safety use case, the system automatically detects where people are below and ensures that dangerous weights cannot be lowered by the crane without syncing with the operators on the floor. For one of the most busy shopping streets in the heart of Europe, Antwerp, Belgium, Robovision can estimate how well social distancing measures are being followed by the population. We provide a dashboard to city services, as shown in this slide. In large essential infrastructure sites, like this Dutch railway station, the mass analysis of tracklets with the help of Ray could help infrastructure providers with new insights when buildings get too busy. Road signalization could be improved with generic anomaly detection, as is shown in this Robovision tunnel safety case. On the healthcare level, Robovision is active in different domains. For instance, in elderly care, we apply AI on the edge to make sure that elderly people can stay for a prolonged period at home when they grow older. When they fall on the ground and are in an emergency situation, this lamp can detect their pose and alert family or friends or the emergency services without the need of a battery-powered wearable. The NVIDIA Jetson-powered lamp fits seamlessly in the household and respects the privacy of the people inside the house or apartment. On a diagnostics level, together with the Netherlands Cancer Institute and the Spanish company called Quibim, Robovision created a consortium to collect anonymized CT data from COVID-19 patients, with the goal of building a fast, cloud-based deep learning model that can rapidly screen the lung percentage affected by COVID-19. Radiologists from all parts of the world are annotating COVID scans on our platform. It's a scalable, cloud-based architecture based on Array, where patient data is uploaded to an Azure data center. This data center is being dispatched to radiologists that can annotate it. And finally, the labeled CT scan dataset is used on a supercomputer to build a 3D deep learning model. The last vertical I want to talk about is manufacturing, where with RVI, we're mainly focused on scalable quality control tasks. For instance, in semicon, where RVI is being used as an OEM software component on electron microscope installations. Early bakes of new chip prototypes often contain many different unknown errors that need to be clustered and analyzed to know where the physical processes went wrong. Unsupervised learning algorithms can guide researchers into this jungle of chip anomalies. The complete platform can run in an air-gapped environment often needed in the secretive semicon R&D labs. Other applications in semicon are doing quality control tasks on wire bonding machines. With scalable semantic segmentation models, we can check if cables are correctly soldered to the pad. Sometimes we need to generate artificial data with our platform in order to simulate situations that cannot be reproduced in an easy way in reality. In this case, a metal shredder is shredding all kinds of metal constructions, but it may never process gas bottles for obvious reasons. Gas pipeline surveillance is another beautiful case of AI at scale. In the direct neighborhood of a gas pipeline, construction work needs to be done in strict cooperation with the pipeline infrastructure provider to prevent calamities. Frequent helicopter flights are getting enormous amounts of data to be screened by cloud-based AI models that can scan for rogue construction workers. And as a final use case, I would like to highlight that we're also contributing to environmental projects like the ocean cleanup. Our platform is being used to process different kinds of plastic and make sure that AI-based sorting can already happen at sea. I hope in all of these slides you have concluded that AI at scale is no longer a thing of the past. AI is already used in a wide variety of use cases nowadays. We will see new kinds of platforms arising integrating a lot more business requirements. With Robovision, we're building one on top of Ray, and we're truly happy we're part of this great open source project, not only as an end user but also as a contributor. I hope there are some interesting questions we can discuss.